All right, so we're on to 3.2. Now we're going to start talking about the inverses of exponential functions, which is a logarithmic function, or log. So for every function, we have an inverse. We already talked about the inverse of an exponential when we looked at the horizontal line test. We knew some things about it, but now we're going to actually dig into logs, those opposite operations. So our essential questions for today, how can I recognize and evaluate logarithmic functions with base A, so A is just a number again, and then be able to make a graph of them. So that's our essential questions for part one here. Some common vocab things that we need to to keep track of, pun intended, I guess. Common log versus natural log. Do you remember what the difference is? So common logs versus natural logs. Common logs are logs that have a base of 10. They call those common logs because that's like our number system. We have a base 10 number system. Think of our place values, ones, tens, hundreds, thousands. Every time you move a place value, it's a power of 10, which has to do with exponentials. So that's kind of where that's coming from. So it's a base 10. When you write them, normally we write LOG as our abbreviation, then we have a little subscript. Normally then that would be a 10 if it was a base 10 log, but because it is so common, they don't do this. They just write LOG usually, and they are assuming that you know that that operation then is base 10. So, and make that assumption when you see just LOG. Natural log, think about what the natural exponential function is. That's E. So these are any logs that have base E as their base. So again, I guess typically you would expect then LOG with like a little E down there. Again, that is not the symbolism that they've chosen to use. Usually what we see is ln. So ln is the natural logarithm, kind of backwards abbreviation there, but if you think about that. So when you see ln on your calculator, that is a base E logarithm. So just FYI. All right, so let's talk about what are logs. So it looks super complicated when we write these out, but we want to think about what the difference is between exponentials and logs. So they're going to give us all this complicated things to think about. So I'm going to go back to an exponential. So if I write something in exponential form, what I'm talking about is y equals some base, some a value to the x. So this is the exponential version of an equation. So exponential, notice the variable x is in the exponent. That's our dependent variable. Do you remember from chapter 1 how we find an inverse? How do you find the inverse of a function? Well, you take the domain and the range and you switch them. So the x and the y get switched. So the domain becomes the range becomes the domain. So that technically is the inverse, and so this would be a logarithmic function. So not very user friendly, right? Because we would never be able to type that into our graphing calculator. We want to be able to solve it for y. So in log form, it looks like this. It would be y equals log base a, because notice the base is a, of x. So being able to type it in, this is the user-friendly version, but it means the same thing as this, just literally switching the x and the y, the domain and the range. So notice the output is going to be equal to that log there. So that's what it means to find a logarithmic function. So let's go back to the definition, the way they have it, some things to think about. The base can't be 1. Again, that's not very interesting. Notice the switch domain and range here, x equals a to the y. Technically, that is the inverse, but again, much easier and much more user-friendly. We would write it as y equals log base a of x. This x is called the argument. When we talk about the thing on the inside there, so it's like the number that we're trying to make, the argument, they say that x value is always going to be a positive number. So the argument, the thing that we're having on the inside there, is always going to be positive, along with the base is always positive. So that base value is going to have to be a positive number as well. We don't have negative bases. So how you read this is you would say log base a of x. So if you're going to say that out loud to someone, that's the inverse of an exponential, log base a of x. So if I'm going to see that, the answer for this is always the power, the exponent. Notice where the y is in this statement. The y value, or the output, is the power or the exponent. So logs, the best way to remember what logs are, they are exponents. It's what power do I raise something to get an answer, that argument. So logs are exponents. That's the best way to describe it and think about it. And logs is the inverse, or the opposite operation of our equation y equals a to the x. So it's the inverse of an exponential. So The answer to a log sentence is an exponent. So the value is an exponent. It's the inverse of the exponential function. So logs and exponentials are inverses of one another. So they have lots of different properties because they're inverses, and that's what we're going to be looking at today for this part one. So an equation, if you see it read this way, x equals a to the y, that means they took the domain and the range and they switched it, right? They switched the x and the y, and that's the same exact thing then as log base a of x. This is the user-friendly function notation that we're going to be using, or sometimes you would say f of x equals log base a of x if you want to actually be in true function notation. It's the way that we can type it into our calculator, but that's where that sentence is coming from. It's just from switching the x and the y, the domain and the range. So when you're evaluating a logarithm, remember that the log is just the exponent. It's the power that you're raising that base to get that argument or that answer. So that means that log base a of x is the power to which a must be raised to obtain x. And that goes right back to this original situation right here. A to what power gives me that x for my answer? So if that's an easier way for you to think of it, that the exponent is the power that we're raising it to, that's what we're finding when we find logs. What power do we raise it to? I want to get you comfortable going back and forth between the two different formats. So I'm going to do a couple examples with you. What would be the equivalent sentence in log form to go with exponential? We do this all the time when we talk about functions and their inverses. Like you might start with multiplication. So like 3 times 2 equals 6. That's a multiplication question. As an inverse, as a division, you might say 6 divided by 2 equals 3. It's the same relationship, just expressed using the inverse instead. Or you might say 6 divided by 3 equals 2. We'd be getting back to that same multiplication. 3 times 2 is 6. So they're just two different ways of writing the same info. That's what I want to be able to do with you for exponentials and logs. So exponential, let's take a really easy exponential scenario here. So 9 equals 3 squared. Or if you like to start with 3 squared equals 9, whichever way is easier for you to look at, that would be like a to the x equals y, if that's a simpler way for you to look at it. What would that look like in log form? So what I'd like to do and think about it for these going back and forth is I like to think of a circle. For me, that's the easiest way to kind of think about it and write it out. So 3 to the second power equals 9. So the 3 is the base. The 2 is the exponent or the power, right? And this 9 is the number that you get for your answer or that argument that we were talking about. So that's that value. So what would that look like in corresponding log form then? So it would be log. That's telling everybody that's the inverse. Base, okay, well the base comes next. Well, the base is 3, so that's a subscript, smaller, lower. So log base 3 of what number? So let's follow the circle around here. Of 9, that's the argument, equals, finish off my circle here, the second power. So the log answer is always going to be the power of the exponent. Notice that's what the log is equal to. What power do I need to raise the base to get 9 for my answer? So I think of it in a circle when I do that. For some people, that's a little bit easier to deal with. So let's take a look at another example like that so we can try another one. So 4 cubed equals 64. True sentence, 4 times 4 times 4. That's log or exponential form. Let's think about the circle as we go around here. How would I write that as a log? Well, it would be log. Base would be, see if you can write it out. Pause the video, see if you can try it. So log base 4 of what number? 64 equals power of 3, so third. So when we go back and forth, I want you to be able to be comfortable. Let's try going the other direction. Let's start with a log. So log base 2 of 8 is equal to, let's see if you can see what this means. That means 2 to what power gives you 8? 2 times 2 times 2, that would have to be 3. True sentence for log. So log base 2 of 8 is equal to 3. Notice how I said that. Log base 2 of 8 of the argument equals 3. What would that be in exponential form? You can do the same thing, this lovely little go around the circle here. So 2 raised to the third power would give you 8. So you should be able to go back and forth. It's just two different ways of representing the same information. All right, so we have lots of ground to cover here. So how can we use the definition of log or understanding what it is to solve some easier scenarios? So let's first of all think about, what does that mean? When you see log base 5 of 125, what is that asking you? It's asking you 5 to the what power gives you 125. That's what it means. So a lot of times what people will do is they'll set this equal to something. They'll give it a value so they have something to like actually talk about here. So they'll set it equal to something and then see if they can rewrite it as an exponential to think of it as an inverse. Sometimes that's easier to do. So if you think of this, rewrite it as an exponential, that means 5 to the what gives you 125. Now if that's a nice answer, awesome. If it's not, we're going to have some more algebra to be able to deal with that. So is 5 or some multiple of 5 going to be, or some power of 5, 125? Well, it sure is. It's 5 cubed. So we can use that one-to-one property that we talked about from before. So 5 cubed is 125. So you can think of it like this. 5 to the what equals 5 to the third. Remember, when they're equal and the bases are the same, then the powers must be the same as well. This would have to be equal to 3. So we'd have a really nice way to do that if those numbers are easy. All right, let's try another one. So sometimes the numbers get a little bit harder. So what is this question asking you? Again, I'm going to set it equal to something. Log base 5 of 1 over 625. That means 5 to the what power would give you 1 over 625. Well, whenever you have a fraction, what kind of exponent would that mean? Is 625 a power of 5, first of all? How many 5s do you need to multiply together to get 625? Guess and check a little bit there. That is equal to 5 to the fourth, but notice where it is. It's in the denominator. So what kind of exponent does that reciprocal? That would be the same as 5 to the negative fourth. So that must mean, again, one-to-one property. I can write both of these as a power of 5. That must mean that x is equal to negative 4. So see if that makes sense then. 5 to the negative fourth power would be equal to 1 over 625. Well, for sure. 5 to the negative fourth, that means 1 over 5 to the fourth, and 5 to the fourth is 625. So rewriting as an exponential can really help. Whenever you see that fraction as your argument, it must mean that it's going to have a negative exponent, right? That's the only way we can get that 1 over. All right, this one's kind of goofy too. Let's take a peek at this one. Log base 125 of 25. What would that be equal to? So again, you're asking the question, 125 to the what power would give you 25? Now this is kind of goofy. How could you possibly have a base raised to a power where your answer is smaller? Usually the base is smaller than what our answer is. So how could that happen? What kind of power must we be raising it to? Can't be a whole number, right? Because squaring, cubing, those numbers get bigger. It must be something that's less. It must be a root, like a square root or a cube root, something like that. So let's see if we can do this with the one-to-one property, though. Can we still make the bases the same? I don't think 125 to any whole number power is going to give me 25. So is there a way that I can write both of these as powers of the same number? 25 is 5 to the second. 125 is 5 to the third to the x. All right, then power to a power we multiply. So that would be 5 to the 3x equals 5 to the second. So again, one-to-one property, if the bases are the same and these two are equal, that must mean that our exponents are equal and I can solve. So I get the 2/3 power, so not a whole number. So kind of hint, moral of the story here, when your base is bigger than your argument, it must be a fractional exponent. So let's try that. Let's see if it works. 125 to the 2/3 power is supposed to give me 25. That's what it's supposed to be saying. Do you remember what 2/3 power means? Remember the bottom is the root. So that's like saying, hey, the cube root of 125 and then squared. All right, so what's the cube root of 125? Well, what times what times what would give you 125? That would be 5. And then square it, and you sure enough get 25. So these work out really well because you can use the one-to-one property. Obviously, not everything can. We'll talk about other algebraic ways to do that as well. But this is just kind of a way to understand logarithms. What do logs mean? You're looking for what power am I raising the base to get that argument. Okay, so let's talk about one that maybe doesn't work out so well. Log base 10 of 300. Don't type anything in your calculator yet. So again, I'm trying to figure out what that's equal to. So I'm going to go ahead and set it equal to something. When you see a log, you're always thinking what power? Okay, so what does this mean? It means 10 to what power gives you 300. So 10 to the what gives you 300. Now, is that going to be a whole number answer? I don't think so. Let's kind of estimate first. What's 10 to the first power? Well, 10. What's 10 to the second power? 100. What's 10 to the third power? 1,000. None of these answers, whole number answers, give you 300, but could you estimate between what whole number or integer values it would be? Well, it's going to be between 100 and 1,000, right? So my answer is going to be between the power of 2 and the power of 3. So it's going to be somewhere between 2 and 3. Which one do you think it'd be closer to? Which one is 300 closer to? Maybe a little closer to 2 than it is to 3? How would you solve that? Okay, well, it's a base 10. This is what we would call a common log. So this is a common log. So thankfully, because it's a base 10, I have a button on my calculator for this. So let's take a peek. LOG, so the one right here, remember our base 10. Now they emphasize, they normally wouldn't write the 10, but they're just saying, hey, psst, hey, this is common log. So if I want to do log of 300, I would literally type in log of 300. 2.477. I'm going to go out to 3 places here. So this would be equal to about 2.477. Now, how about if you wanted to check your answer to see if this was correct? That the power that I raised this to is exactly 2 point whatever, whatever, whatever. So let's check our answer. 10 raised to the, I'm going to go ahead and grab my answer so I can get all the digits. And there's your 300. If you round, it won't be quite exact, but you could tell that you're in the right ballpark. So not every one of these can we use 1-to-1 power for, right? Because 300 is not a power of 10 by itself, but we can get close with a decimal answer. But you're still looking for what power do I raise that to? All right, well, we can do all sorts of solving then by using inverse operations, and that's really what the rest of today is going to be all about until we get to some things with graphs at the end. How can I use exponential and log inverses to help solve? So let's take a look at this one. Log base 7 of x equals 1. Solve it for x. You're looking for the argument. So not the power. You know what the power is. The power is 1. Sometimes the easiest way to solve an equation is by using its inverse. Can you rewrite this for me as an exponential equation instead of a log? Well, the base would be 7 to the first power equals our argument of x. Well, gosh, solving for the argument, you just have to do that power. So what's 7 to the first power? 7. Yep, and let's see if that makes sense. So the log base 7 of 7 equals 1. So 7 raised to the first power would give me 7. Absolutely. So when the base and the argument are the same, the power you're looking at is always 1. So use the inverse. That's the idea here. So we write it as an exponential. So it's a much easier way for us to solve. We just have more skills to be able to deal with that. So write it as an exponential to be able to solve. So here are some properties to keep in mind then that'll be helpful when we're using that idea. So we're going to go through each of these and see if we can come up with what would be true for all of these. Are all going to be things we use when we solve. So let's look at property number 1. It says log base a of 1 equals. Okay, so this is a little bit different than the one that we just did. I'm going to go ahead and for this one, try to see if we can solve it and figure out what this would have to be equal to. So log base a of 1 is always going to be what? Okay, so I'm just going to go ahead and put a little x here so we can rewrite it as an exponential to talk about it. So I'm going to rewrite it as an exponential. A to the what would be equal to 1. Now you may be thinking I got too many variables going on here, but what's the only thing that when I raise it to a power, what power would this have to be to get a 1 for my answer? If my answer is 1, what power does that number have to be raised to? Always is the 0 power, right? So any number raised to the 0 power is 1. So that means that this log base a of 1, if your argument is 1, that always has to be equal to 0. So look for an argument of 1 that would always have to be a 0. It's an easy thing to look for if you know it's true. All right, let's take a look at the next property. Property number 2 here. Log base a of a. Again, I don't know what that's equal to. Maybe you do, hopefully. I'm going to set it equal to something so I can actually solve. So let's do a rewrite here. So I'm going to rewrite this as an exponential. A to the what would equal a. A to the what power would equal a. I'm going to go ahead and write in what this would be. If there's a with nothing written there, that means it's a power of 1. 1-to-1 property. If the bases are the same, I don't care what a is, 7, whatever. What does this exponent have to be? Well, it has to be equal to the other exponent, which means the x would have to be equal to 1. So that means the log base a of a is always 1. That's the exact same example that we just did. When the base and the argument are the same, that's where you get a 1 for your answer. So that's where that's coming from. So if you have your argument and your base is the same, it's got to be 1, right? A to what power gives me a? The first power. So it works out really well. All right, let's take a look at the next two. Let's take a look at 3 and 4. So I'm going to get rid of this so we have some room to work with here. Let's take a look at the third property. This is a great one. Log base a of a to the x. Looks like we have a lot of a's going on. We know log base a of a is 1, which is pretty spiffy. That's going to be part of this conversation, but I'm going to make up a number example so we can actually work with numbers. Let's do this one so we can actually think about things that are easy for us. Log base 10 of 10 cubed. So notice these two numbers are the same. Can we solve this? What's 10 cubed? 10 times 10 times 10, it's 1,000. You can type this into your calculator, otherwise think it through what this would be equal to. 10 to the what power gives you 1,000? Well, the what power has to be 3, doesn't it? So look back in the original equation here. Log base 10 of 10 cubed, the answer is 3. So log base a of a to the x would have to always be x. In other words, when the base of the argument are the same and it's raised to a power, your answer is always going to be whatever that x value is. And you're going to see a very similar outcome for this other part of number 3 here. A to the log base a of x. I'm going to do the same thing. We need a number example. So how about 10 to the log base 10 of 100? Let's see if we can solve this one, and then we'll be able to see what that answer should be. What's the log base 10 of 100? That means 10 to the what gives you 100? Well, 10 squared gives you 100, right? So this would be then 10, this is squared, and what's 10 squared? 100. In other words, the answer to this whole crazy looking thing was 100. So 10 to the log base 10 of 100 was 100. So a to the log base a of x would be x. In other words, they undo each other. So in both of these examples for number 3, if the base and the two bases are the same, so log base a of a to the bases are the same, a to the log base a bases are the same, they undo each other and you just get x. Think about what opposite operations do. Like if you times a number by 3, then divide it by 3, you get back to the number you started with. So if you do base raised to the and then log same base, you're going to get back to the number that you started with. So that's all that's saying. It looks way more complicated than that, but if your bases are equal, then you're going to end up with whatever that number is. All right, let's take a look at the last one. This is the equality property, and I think this is pretty self-explanatory. We had a one-to-one property for exponentials. We also have it for logs. If you have two logs that are equal, super important, the bases are equal. So the bases are the same, so the bases are equal here. Then what would also have to be true? Well, then their arguments would have to be equal as well. The x would have to be equal to the y. This is that one-to-one property that we had also for exponentials. So that's really critical when we're solving. So let's take a look at some of these and see if we can run through a few of them here. All right, so I want you to pause the video for each of these and see if you can figure out what's happening. So we're going to go through each one of these. Simplify log base 9 of 9. Set it equal to something and see if we can solve. So 9 to the what power would give you 9? What makes sense? Would have to be 9 to the first. In other words, 9 to what power gives you 9? It would have to be equal to 1. So the log base 9 of 9 is most definitely 1. Take a look back at your properties. That's taking a look at your property number 2. So that's all that's saying. So it's an example of that. All right, let's take a look at the next one. Looks super complicated again. 20 to the log base 20 of 3. So bases are the same. They undo each other. Final answer should be 3. We are looking at the second part of that number 3 property. We're looking at this one right here. So if the bases are the same, they undo each other. So if you notice that, it's way easier because that looks kind of crazy. This one, simplified log base square root of 3, kind of a weird base, of 1. So square root of 3 to what power would give you 1? Well, what's the only exponent you can raise something to get 1 for your answer? It'd have to be 0. So we're going back and we're using that very first property. So if you have 1 as your argument, it's got to be 0. There's the only way that that's going to work. All right, let's take a look at the last property. So we've illustrated all the other ones. It says solve this for x. Notice you have logs on both sides, and this is really important. That's the equality property then. If the bases are the same, which they are, then their arguments would have to be the same as well. So we're going to be careful that we can solve for that. So this is a secondary equation again. Most of the time I'd say, hey, solve it by factoring, but there's no other variable term, so I would just go ahead and subtract the 3 and square root, And in this case, we get plus or minus 3. So both of those numbers, when you plug them back in, remember your arguments are supposed to be positive. So when you plug your number back in, this thing is supposed to be a positive value. If you square either positive or negative 3, you will get a positive result. So both of those would be solutions. So the equality property works really well. So take a peek at another equality property again. Are the bases the same on this one? There's nothing written. What kind of log is that then? Well, that's a base 10 log, so they are equal. So that means 4 minus 3x would have to be equal to x plus 2. And again, we can solve, so we can just move those terms. So we'd add the 3x, subtract the 2, so we get x equals a half. Be careful when you're dividing. And the number that we plug back in would make those arguments positive. We know we're okay. So it's an equality property to be able to solve. All right, let's talk about graphs now. So we'll finish up today with a couple things on graphs. To sketch the graph of a log function, we're going to use its inverse. So we're going to talk about what the inverse graph is. So in order to be able to graph y equals log base a of x, we're really going to think about what its inverse is, y equals a to the x. We're going to use the exponential. And remember, if you graph a function and its inverse, do you remember the symmetry that those two graphs have? Think back to what we did before for inverses. They are reflections over a line, and the line is y equals x. So it's a great way to be able to check and actually solve and find those. So to make that sketch, we're going to be doing a little bit of switch the domain and the range. So switch the x and y to be able to graph those points. So we can graph the points then for that inverse. All right, so let's take a look at an example here. How would you graph log base 3 of x? So if I'm going to try to graph that, I'm really going to think about what its inverse graph looks like. So I'm just going to call it something else just for conversation purposes here. Remember, this is like y equals log base 3 of x. We switch the x and the y, so that means it would be r3 to the x power. So again, this version of our log sentence is really x equals 3 to the y. So when I find the inverse of it, I switch the x and the y, and we get our inverse equation, which is exponential. So if it's easier to see it that way with the y equals, I'm just going to call it g of x just so it's not f of x. So the original function that I'm trying to graph is the log one, but I'm not exactly sure what the log one looks like. So I'm going to graph its inverse, which is the exponential. And then I'm going to use what I know about the graph of exponentials and logs because they're inverses. We can remember what symmetry that has, and that's going to make it a lot easier to graph. So a lot of times if I'm making a sketch, I'll graph exponential first. So let's go ahead and just pick easy numbers. Remember the domain for an exponential, all real numbers. So we're going to do 3 to the negative first, 3 to the 0, and 3 to the first. So 3 to the negative first, that would be a third. Anything to the 0 power is 1. 3 to the first is 3. So this is not the final graph that I'm looking for. This is the inverse function. So this is the exponential version. So we have 1, 3, and then we have negative 1, a third. So this one is my g of x. So this is the inverse. So this is y equals 3 to the x. All right, so when I graph its inverse equation, log base 3 of x, that means my domain and range are switching. So they have this symmetry over the line y equals x. So that means I can switch the ordered pairs. Remember, we did this before. That's how we graphed inverses. So it'll be 1/3 negative 1, 1, 0, and 3, 1. So 1, 0, 3, 1, and 1/3 negative 1. And we're going to get a graph something like this. And remember your symmetry that we talked about over the line y equals x, 1, 1, 2, 2, 3, 3, 4, 4. So there's your symmetry or your fold line, and this is your f of x equals log base 3 of x. So that relationship is always true between a function and its inverse. Some things to think about. Remember how we always had a y-intercept on this original graph of 0, 1. Well, guess what? Then we have an x-intercept on our log graph of 1, 0. These are key features of log graphs. Remember how we had a domain for the original function of g of x? The domain was all reals. That means the range or the output is all reals for your log, because remember domain and range switch. So the domain of one becomes the range for the other. Okay, do you remember what the domain was? or the range was for the g of x, the green one. It was only the values above the x-axis, so only the positives. So guess what? Look at your red graph. It's only the positives for the x. So the domain is 0 to infinity. They switched, right? They're the exact opposite of what it was for exponentials. And then does it have an asymptote? Sure it does, but it's not the x-axis anymore. Look at the red graph. What does it have as an asymptote? It has the y-axis. So the asymptote is the y-axis, or x equals 0. So it's very much whatever was an x becomes a y, whatever was a y becomes an x. They interchange, they switch. So it's a really easy way to see that relationship. So let's talk a little bit then about what we just noticed. So I want you to look back at your red graph to answer these questions. And it says for the a value greater than 1. So what they mean by that is the base that you're using, our a down here, the base has to be bigger than 1. Is this graph, the red one, increasing or decreasing for its domain? Well, the red is going up, so this graph is definitely increasing. So it's increasing for its entire domain. For this graph, so the log base a of x, where again the a has to be greater than 1, what was the domain? Well, it was only positive numbers. There was nothing to the left of the y-axis. We only had values going this direction. This red graph is only in quadrants 1 and 4. So it's only positive, so 0 to infinity. The range, it went everywhere, so negative infinity to infinity. Remember, it's the exact switch of what it was for exponentials. And the x-intercept, now notice x-intercept is 1, 0, because remember in an exponential it had a y-intercept at 0, 1. And then also the graph has a vertical asymptote. That's the y-axis. So that x equals 0 equation is its vertical asymptote. So everything that was an x becomes a y and vice versa. All right, so I want you to think about transformations now for logs. It works the same way as it does for exponentials. So anything in terms of transformation and moving around will be true. So I want to do the same thing as what we did before. If this is our parent graph, so we're using that as a parent graph, how would you make the graph go right 3? Remember, left and right is horizontal. It needs to be in with the x. Our x is the argument on the inside there. So this would be, oh, I'll make up one, g of x. We'll pick different function names here. Log base 3 of, notice what I'm doing, parentheses, so important. It has to be in with the argument. If I want to go to the right, that means x minus 3, because remember, if I'm going to the right, I'm seeing how far am I away from 0, right 3, positive 3, x minus 3. Super critical that you have the parentheses in there. How would you go down to? Let's call that h of x. Going down to. Well, the vertical shift is outside of the argument, so it can't be in with the x. So you got to be super clear here that down to is on the outside. Some people even, just to be clear, they'll put parentheses around it. Your graphing calculator will do that, by the way. All right, how would you reflect over the x-axis? So think about x-axis reflection. That means your output or your y changes sign. So I'll pick a different one, m of x here. That means the output or the answer, so out front. So it would be opposite log base 3 of x. It would be flipped over. So instead of being the x is above, they go below, the x is below, go above. Where would you put the negative if you wanted to flip over the y-axis? What would that look like? If it was over the y-axis, well, that means the x value would have to change sign, which means it has to go inside with the x. So just be careful that you know the difference. Everything that you're normally accustomed to seeing will be the same here when we talk about the shifts and the transformations. All right, so here's what I'd like you to do. Can you tell me what shifts are going to take place for letter A and letter B here? And we're going to try to make a really quick sketch for each one of those. So take a look at letter A. Notice what the value is. What would happen to your graph of log base 3 of x? If there's a -1 outside the argument, that means it's going to go down 1. Notice that they put it before instead of after, because sometimes if you write log base 3 of x -1, people could get confused. Like, did you just forget your parentheses? Did you not? So if you really want to be careful, you can put that -1 in front. Okay, so let's talk about what happens to everything when we do this. Your vertical asymptote, if you move the entire graph down 1, is not going to change. We're going back to that parent graph that we graphed just a moment ago, the red one. I have it over here graphed as the blue one, though, so be careful. Remember how you had a 1, 0 for your x-intercept point? Well, it's no longer going to be at 1. We went down 1, so it's going to be right here. I'm just going to make a rough sketch, and it would be something like this. So that's just down 1. I'm going to make a really quick sketch. Okay, what's going to happen in letter B? Notice it's inside with the x. Make your prediction. What's going to happen? x minus a negative 3, this should be a left 3, because remember, if you set this equal to 0, what's my shift? I went to the left 3. Okay, so think about what happens to the asymptote. We have a vertical asymptote at 0. If I shift this graph left 3, that means I'm actually going to be moving my asymptote. So instead of being at 0, it's going to be at 3. So this one, the horizontal shift affects the asymptotes, just like in the exponentials, the vertical shift did. All right, now remember where your intercept was. It was at 1. It's going to go 3 to the left, so it's going to be over here at negative 2, and that'll be enough to get us a pretty decent sketch. If we wanted more points, we could definitely do that. So being able to understand logs come from being able to understand exponentials. We use this inverse idea, switching the domain and the range from our exponential. Remember, it has that symmetry y equals x. All right, so back to our essential questions. Being able to recognize and evaluate log functions using all those log properties, and then being able to make a sketch of a log. Use its exponential, and we can switch the domain and the range.